Hello, everyone. So I think now it's time for our second talk in this morning. We're happy to have Professor John Ellis to give us an overview talk on Higgs boson and beyond. So John has been well known to probably most of you, and he has been a big expert on Higgs boson. So I would mention one of his pioneer work leads to the discovery of by two experiments actually on gluon. And after Peter Higgs and Eglet and brought the proposed this Higgs boson in a toy model of the U1 gauge theory, and Sten Weinberg was the first to build this Higgs boson into the electroweak SU2 cross U1. And John and his collaborator were the first to put the Higgs boson on collider and show people how to produce and discover Higgs boson. And very fortunate, 40 years later, 2012, we do have a Higgs discovery. We did have Higgs discovery at the LHC. And let's John to say, John, what will tell us today about Higgs boson and beyond. Let's welcome.
Yes. So thank you very much for the invitation. It's good to be back at BIMSA, that's second ICBS. And I'd like to thank Tal Han for giving an introduction to many of the topics that I'm going to be discussing in my talk. So I'll start off by reviewing what we currently know about the couplings of the Higgs boson to other particles. And we actually now have the first evidence for a quadratic Higgs coupling, which I think many people are unaware of. I commented on that in Tao's talk. I'll go into that in a little bit more detail in my presentation. Then you may be somewhat baffled by the third line in this outline, but I'll explain that a bit later. So I think as Tao has already explained, there's many motivations for physics beyond the standard model, and a number of them involve mysteries associated with the Higgs boson. I'm not going to belabor that point too much. Going to spend a bit of time advertising the standard model effective field theory as a sort of a broadband way of searching for possible new physics beyond the standard model. And at the end, I'm just going to put in a little bit about well, first of all, MW, and then later on about G-2 as being possible indications from experiment of physics beyond the standard model. Okay, so I waste one slide just showing you what the standard model is. A bunch of random quantum numbers. Before the LHC got started, the top two lines of the Lagrangian had been explored with better than per mil precision in many cases at previous experiments. And we're now in the business of testing the two bottom lines, for which there was absolutely no direct evidence before the LHC got started. So currently the precision is a level of maybe 10%, but as you heard from Tao's talk, we hope in the future to be able to carry that precision much better. So you may have noticed subliminally on my opening slide that I had a little logo in the bottom left-hand corner. This is the 70th anniversary of the birth of CERN. I'd just like to point out that it's also the 60th anniversary of the birth of the Euler-Brout Higgs mechanism. And so I just selected this little picture which shows both of them when they were getting a prize some years ago. Peter Higgs didn't turn up for the prize ceremony, but here he is working away on his theory. Unfortunately, most of these founding founders of the BH mechanism are no longer with us, but they are in spirit. So as Hongjian generously mentioned in his introduction, I personally got interested in the Higgs boson in 1975, and together with Mary Gaillard and Dimitri Nanopoulos, we tried to make a sort of systematic review of what a Higgs boson would look like in various different types of experiment. Although back in those days, it was still regarded as being a very speculative idea. And that's one of the reasons why we wrote at the end of our paper, we do not want to encourage big experimental searches for the Higgs boson. And it would have been premature back in 1975. But of course, later on, CERN built the LHC. Experiments did not take our outdated advice, and they made a big effort to search for the Higgs boson. So in our paper, we discussed very briefly associated production of the Higgs with a Z. And then a few months later, there was the first review of the possible physics that you could do with LEP. And Mary Gaillard and I put in a bit more discussion about looking for Higgs plus Z. But other people also had the idea of looking for Higgs plus Z, I should mention. In particular, Jose and Yoffe in Russia. Yeah, we're probably getting a little bit off topic, but yes, indeed. So I've often said that that was maybe the most expensive calculation that I ever did when I calculated the mass in supersymmetry and found that it was too heavy to be reduced at LEP. So there was an attempt to convince the management of CERN to push LEP just even a little bit further, but didn't happen. So this is a picture I like from Higgs Dependence Day. July the 4th, 2012. And here you see Peter Higgs meeting, apparently for the first time, Francois Englert. And here you see Fabiola Gianotti, who presented the discovery of the Higgs boson on behalf of the Atlas collaboration, and of course is now Director General of CERN. So no glass ceiling at CERN. Okay, so this is a summary of LHC measurements, generally in the standard model, production of Ws, Zs, tops, jets, etc., etc., etc. And here in the middle, you have a compilation of measurements of Higgs production. So what you see here is that the theoretical calculation, certain uncertainties, generally overlaps with the experimental measurements. So everything is consistent with the standard model prediction. So one way of presenting those results is to say, well, look, the coupling of the Higgs to other particles should be proportional to their masses. So let's test that. So particle masses on the horizontal axis, vertical axis is the coupling of the Higgs. And you see that the standard model predicts a linear dependence, and you see that all the measurements so far are consistent with that, including most recently the measurement of the coupling to the muon, which I remind you is more than a factor of 1,000 different than the coupling of the Higgs to the top quark. So when we produced a plot like this, with my then PhD student, Terong Yu, we wrote in our paper that it walks and quacks like a Higgs boson. That was true in 2013, and it's still true. So one or two interesting recent developments. So one development has been the report last year by Atlas and CMS of evidence for the decay Higgs into Z gamma. And I find this amusing because it's the first example of a decay of the Higgs into something which is not a particle-antiparticle pair, or for that matter, a particle-particle pair. Of course, it's a loop process in the standard model. So far, the signal for this is, quite frankly, not terribly impressive. It corresponds to a signal strength 2.2 plus or minus 0.7 times the standard model value. So you might ask, how accurate is the standard model calculation of this decay mode? could the fact that the central value is somewhat higher than the standard model prediction give some space for some physics beyond the standard model? So together with some colleagues towards the end of last year, we did a higher order QCD calculation just to check that that doesn't affect the interpretation of the data. And we indeed found that higher order QCD is unimportant. Other people have calculated higher order electroweak corrections. So is this BSM physics, this 2.2, or is it just statistics? Probably statistics, but no, you can always dream. And whenever I ride along in a car in China, I see these cars saying, build your dream. So let's keep on building. Yeah, so these are some of the diagrams that we included in our calculation. Here you see how the signal strength changes when you go from leading order to next to leading order QCD. And there's an interference effect, which is actually negative, but it's been expanded here by a factor of 10. It's only a 3% effect on the total production rate for Higgs intersect gamma. Okay, now another somewhat novel topic in Higgs couplings. So standard model Lagrangian contains higher order Higgs couplings, so the triple Higgs coupling, I'll discuss that. But there's also a VVHH coupling. So the VVHH coupling is a part of the Higgs kinetic term, and that has to be there. And the normalization is actually fixed by the normalization of the VVH coupling. And if it were absent, or if it were modified, then the consistency, the normalizability of the standard model would be destroyed. Of course, there could be modifications of both the triple Higgs coupling and the VVHH coupling by higher order terms in the effective field theory. So let's parameterize those couplings by coupling modifiers kappa lambda and kappa 2b, and then what can the experiments tell us about the possible experimental values? So these are generic diagrams for doubled Higgs production. The top two were the ones that Tao showed in his talk. There's a bunch of other ones as well, including this VVH coupling here. You also get sensitivity to the triple Higgs coupling from radiative corrections to single Higgs production. And here's some diagrams for that. So these are for some results from an Atlas analysis a couple of years ago, where they established a limit on double Higgs production, and they used that to constrain the triple Higgs coupling. They in fact included in their analysis both the effects of the triple Higgs coupling on double Higgs production and also single Higgs production. Now, more recently, Atlas and CMS have also analyzed their data to look for Higgs pair production in a sort of boosted kinematics where they're widely separated in rapidity. And production in that kinematics is sensitive to the two-vector, two Higgs coupling. And as you can see here in the CMS analysis, the data are quite consistent with the standard model prediction. And the possibility that that coupling is absent is excluded at something like the 5 sigma level. It depends a little bit on the assumptions that you make about other Higgs couplings. But vanishing VVHH coupling is strongly excluded. And this is a similar analysis by the application that came out last month. So they, for example, quote, modifier with a two Higgs coupling, which is 1.02 plus or minus 0.23, if all other Higgs couplings have the standard model values. And it would be able to, yeah. Sorry? So you're most sensitive to the VV-HH coupling when you look at boosted kinematics, when the Higgs are widely separated in rapidity. And you don't see many Higgses, don't see any significant evidence for Higgses in that configuration. That immediately tells you that this coupling has to be there in order to cancel out the other diagrams that exist in the standard model. Okay. Now I come to what for many of you will have been the most puzzling line in my introduction. Will the LHC discover a boson with a mass of 340 GeV? So what am I talking about? What I'm talking about is pseudoscalar toponium. So it's of course predicted to have a mass a few GeV below the TT bar threshold. And here on this picture here, you see a calculation of various different contributions to TT bar production. So here's the total cross-section in green. Most of the production is in a color octet state, but there's also a contribution from a color singlet TT bar state, which is actually dominant around threshold. And in that color singlet channel, you get, in principle, a pseudoscalar toponium pole. Now, it's not been studied in great detail at the for the LHC. The corresponding signal in an E plus E minus annihilation is vector toponium, which has been studied in great detail. But as I said, there have been relatively few studies for toponium in proton-proton collisions, and I don't want to go through the details of it, but actually a very complicated and, to my mind, very fascinating problem in QCD. So if there's anybody here who fancies themselves at doing complicated calculations in QCD, here's a good one for you. Okay, so what's the status of LHC measurements? So of course, they see lots of TT bar pairs. And generally, the measurements agree with theory, although there have been some issues close to threshold. More recently, they started measuring the angular correlation between the decay products of TT bar. And they've measured a significant entanglement between the decay properties of the T and the T bar. And they got very excited in verifying quantum mechanics, Bell inequalities, and so on and so forth. Bullshit. The interesting feature is that they see a correlation coefficient which is negative, which is just what you expect from spin zero production. So there's two observables, at least, which you can look for at the LHC. One is this entanglement quantity, and the other one, of course, is the total cross-section. And here are a couple of plots taken from a very recent paper by the CMS collaboration. They include both data and entanglement, and they give you fits without including a pseudoscalar toponium state and with the toponium. And if you're really optimistic, you can see that the fit with toponium is slightly better than the fit without toponium. So this is causing a certain amount of excitement in the LHC community. This is only with a small fraction of the total amount of data. It's only one experiment. Put it together with Atlas, 4 times more data already in the can, much more data in the future. Maybe there's a chance of seeing toponium at the LHC. Okay, that's a little bit off topic. Now, if you are a funding agency or maybe a condensed matter physicist, you might say, well, look, now you've found the Higgs boson, you've completed the standard model, there's nothing more to be done. cut off your funding and go off and do biology or something. Well, I would counter that argument with this quotation from the poet T.S. Eliot. To make an end is to make a beginning. The end is where we start from. And the way I interpret that is, okay, you've completed testing, finding all the particles in the standard model, and that gives you a firm basis for thinking about what happens beyond the standard model. It's the start of a new era. And I take as my sacred text for this, this film poster of James Bond, and I modify it slightly, changing the two principal characters, and I give you 007 reasons for thinking there must be physics beyond the standard model. In the standard model, if you calculate the properties of the electroweak vacuum, you find that quote-unquote empty space is unstable. Of course, the standard model doesn't contain a candidate for dark matter. It doesn't explain the origin of matter. It doesn't explain the sizes of masses, etc., etc., etc. So there's plenty of reasons for thinking there must be physics beyond the standard model. I don't have time in this talk to discuss all of them, so I'm going to be quite selective. So a lot of these issues have to do with the Higgs. So here I've written out the terms in the Higgs, in the standard model Lagrangian that involve the Higgs in some way. So the first bunch of couplings here, these are the Yukawa couplings, which we absolutely do not understand. And I have absolutely no idea how to explain the pattern of Higgs couplings to fermions, the origin of CP, etc., etc., etc. So I move on to the next problem, which is the magnitude of the mass term mu here, which Tao already mentioned in his talk. So this is, the magnitude of this term has two actually slightly different aspects. One is why it's so much smaller than the Planck scale, which I would call the hierarchy problem. And the other one is how it stays much smaller despite radiative corrections, so-called naturalness problem. Then we have the quartic coupling, and this is sufficiently small that if you extrapolate to high scales, you find that it goes negative, and that gives you this issue of the stability of the electroweak vacuum. Now here's a constant term, so you might wonder, well, why did I put that in? Because it doesn't involve the Higgs field. But when the Higgs settles from its symmetric high temperature value to the current low temperature value with a non-zero vacuum expectation value, you're changing the dark energy or the cosmological constant by many, 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 many orders of magnitude more than the current value. So in fact, this is, to my mind, a sort of naturalness and hierarchy problem, which is even much more critical than the magnitude of the Higgs mass term. And in principle, there could be additional higher order terms in the effective Lagrangian involving Higgs, and I'll come back to that later. So Tao has already shown you these two diagrams, and they're quadratically divergent, which kind of looks like it means that there would be very large radiative corrections to the effective mass of the Higgs. But you can cancel out quadratic divergence if you have this specific relationship between the scalar and the fermion couplings, which is just what's predicted by supersymmetry. So this is what gave, which generated a whole bunch of excitement 40, 45 years ago when people first realized it. Of course, the excitement level has diminished somewhat with the continuing shyness of supersymmetry, which hasn't shown up yet. Personally, I'm not ready to abandon supersymmetry. It's often said that unsuccessful theories don't die. It's the old theorists who proposed the unsuccessful theories that die. But I'm not dead yet. So I'm still a fan of supersymmetry. And I would even argue that the LHC has provided 3 new motivations for it. Because supersymmetry can stabilize the electroweak vacuum. It made a successful prediction for the Higgs mass. It predicted correctly that the Higgs couplings would be similar to those in the standard model. And this is in addition to the naturalness argument that I presented on the previous slide, the fact that it helps you make a gut, the fact that it seems to be essential in string theory, provides dark matter, and it could explain the anomaly in G-2. So, supersymmetry, where art thou? So I'm not going to say anything about the instability problem, because Alessandro is going to give a full talk about this. I just mention the fact that this problem exists, and to my mind, it motivates the presence of new physics somewhere below the instability scale, so below something like 10 to the 10 GeV, which could be supersymmetry or it could be something else, but it could be supersymmetry. Okay, so I outlined various reasons for thinking that there should be physics beyond the standard model. And of course, we all hope that new physics is within reach of experiments that we could actually do on Earth. So how would we make a broadband search for such possible new physics as agnostic as possible? So this is where the standard model effective field theory comes in. And I've got another quotation for this. This quotation comes from the Chinese strategist Sun Tzu, who wrote 2,000 years ago, "The direct method may be used, but indirect methods will be needed in order to secure victory." So, direct, look for new particles. Indirect, look for the effects of virtual exchanges of heavy particles. The direct and the indirect lead on to each other in turn. It's like moving in a circle. So obviously, he was thinking about FCC or CEPC. Who can exhaust the possibilities of their combination? So I'd just like to remind people that effective field theories have a long and glorious history, in particular in the discovery of the standard model. So back in the 1930s, we had an embryonic dimension 4 theory, QED, formulated by Dirac. But we also had dimension 6 4 Fermi fermion theory of the weak interaction, proposed by Fermi. So I think everybody suspected that this point-like interaction was only an approximation, and that if you went to higher energies, you would eventually disentangle those 4 fermions, and you would probably find the exchange of some massive particles. So for quite some time, there was confusion about what was the precise Lorentz form of this 4 Fermi interaction. In the 1950s, it was established that it was V minus A, current combination. So between those two V minus A currents, there was probably a massive vector boson, which of course motivated looking for a way of formulating a theory with massive vector bosons, hence Higgs et al. Effective field theories also played a role in the formulation of QCD, but that's a more complicated story that I won't go into. Okay, so there's been quite an industry over the last few years of, first of all, formulating and secondly, testing standard model effective field theory as a way of looking for possible new physics at the LHC and elsewhere. So it's quite complicated because there's many possible forms of these dimension 6 operators. I mean, back in the 1930s, they had it easy. It was only SPVAT. A lot more possibilities for the dimension 6 interaction with the standard model. And another complication is that you're not just talking about beta decay, you're also talking about many other processes, many processes which involve the same sets of operators. So for example, one of these operators here contributes to diboson production at the LHC, electroweak position observables at LEP, Higgs production, top production, etc., etc., etc. So what this means is that if you want to use this tool, you need to do a global fit to all the relevant data and analyze them in a consistent and coherent. So we did this a few years ago, and here's some results. I'm not going to go into them in great detail. Take-home messages are that the operator coefficients are all consistent with 0, and the magnitudes of the operator coefficients are sufficiently small that you can say that a characteristic scale for the new physics is at the level of a TeV, or in some cases, even 10 TeV. So, no significant deviations from the standard model, and the new physics maybe 1 or 2 orders of magnitude heavier than the WZ and Higgs. So how would you actually use this analysis? Well, one way of using it is to say, let's consider single field extensions of the standard model. So you add in one field. It might be spin 0, might be a vector, might be a fermion. And you use that previous analysis to tell you what might be the mass of that new field or its coupling. So this shows you some results from the paper we wrote about this. So if you assume unit couplings, then those new fields must weigh a TeV, more in many cases. Alternatively, if you say that the new particle weighs 1 TeV, you get upper limits on the possible couplings to standard model particles. But again, I emphasize that there's no significant evidence for any non-zero coefficient, no evidence that any of these things actually exist, but at least you've got some concrete constraints on them. Well, that was before CDF came along and measured the mass of the W. So as you know, they came up with a measurement that is nominally in 7 sigma discrepancy with the standard model value. Now, many people are dubious about the CDF result. I'm not going to get into that. I just want to use that result as a sort of test case for seeing how the standard model effective field theory could be useful in a case where there was a significant discrepancy between some measurement and the standard model. So it turns out that there's just 4 SMEFT operators that could contribute to changing the W mass. And indeed, if you do the sort of global fit that I mentioned previously, but now switching out the previous measurement of MW, which of course agreed with the standard model, and switching in this new measurement, which doesn't agree with the standard model, then you find that any one of those 4 operators could explain the W mass measurement if it had a non-zero coefficient. Okay, next step. What could generate one of those operators? And so you go back through those single field extensions of the standard model, and there are a few of them that could generate these operators that could change MW. Some of them push MW in the wrong direction, so forget about them. But there are some of them that push MW in the right direction. So if you believed all this, you would say, well, maybe what CDF has discovered is evidence that one of these particles might be within experimental reach. And this shows you for the single field extensions that could contribute to MW, how heavy the particles would have to be if they had unit coupling, or if you don't like unit coupling, you just rescale by the magnitude of the coupling, which you like. So what's interesting is that at least a couple of them are in principle within reach of the LHC or high luminosity LHC. So as I said, I don't believe necessarily in the CDF measurement of MW, but I'm just using this as an example of how you can analyze anomalous data and try to get some idea of where the possible new physics might be. So I like the SNEP because it's a powerful framework to do global analyses of data as a systematic way to look for new physics. What I was presenting was an analysis at the level of dimension 6. Of course, it's got also higher dimensional operators, dimension 8, so on and so forth. And people have started doing global analyses of the data, including dimension 8 operators. But I would like to emphasize that there are some observables which the first non-standard model contribution appears at dimension 8. These are things that do not occur in the standard model, do not occur at the level of dimension 6. First contributions come in at dimension 8. And these include things like light by light scattering, glue go to gamma gamma, and also neutral triple gauge couplings. And so with Hongzhan as my chair, I had to mention a series of papers that we've written about how one could probe the possible existence of these dimension 8 operators by looking at neutral triple gauge couplings, but I don't have time to go into the details. See, plenty of time. Okay, so now I want to talk about one other possible experimental evidence for physics beyond the standard model, namely the anomalous magnetic moment of the muon. So this lovely picture shows the magnet, which is used at Fermilab for the G-2 experiment, arriving from Brookhaven. And is that a dawn of new physics? Or is this the sunset of the standard model? I think it's a sunset, actually, if I remember my Fermilab geography correctly. Maybe it's the sunset of our hopes for new physics. So we've been living with an anomaly in G-2 for over 20 years now. So an issue was first raised by a Brookhaven experiment in the early 2000s. And the Fermilab measurements over the last 2 or 3 years confirm what they had measured, but with a significantly reduced uncertainty. And here's the world average for the anomalous magnetic moment of the muon. A factor of 10 to the 9 has been taken out here. This is an incredibly precise measurement. So how do you calculate the standard model prediction for G-2? So traditionally, the way that this has been done has been to use data on low energy E plus E minus experiments to calculate diagrams which involve virtual hadron production in their contributions to G-2. Because of the mass of the muon is about 100 MeV, the relevant hadronic physics is below a GeV. So here's a compilation from a few years ago of the available E plus E minus goes to hadrons data below 1 GeV. And you see here that indeed this range of energies makes the dominant contribution and also contributes largely to the uncertainty. So these plots are taken from a review article which appeared shortly before the Fermilab result came out. So that's what's shown down here. WP20 is the result on the previous slide. You put that into the machinery and you come out with a prediction for G-2, which disagrees with the old Brookhaven measurement, and R Fortiori disagrees with the new Fermilab measurement. But since that theoretical review was compiled, there have been a number of direct determinations, not involving the use of other data, but direct theoretical determinations using lattice QCD. Most of them, till a couple of years ago, had large errors. But one, called BMW, had a relatively small uncertainty. So I think initially people weren't quite sure how to interpret the BMW measurement. Maybe they were being a little bit over-optimistic in estimating their uncertainties, or maybe there was some other issue. But subsequently, there have been many other lattice calculations, independent lattice calculations, which largely agree with BMW. So maybe one should take that seriously as a new and more reliable calculation of the hadronic contribution to G-2. Now, in the second half of last year, there was another important development. So an experiment at Novosibirsk in Russia came out with a new measurement of E plus E minus goes to pi plus pi minus in the range of energies below 1 GeV. And their measurement disagrees significantly with previous measurements. So their measurement with its uncertainty is indicated by this yellow band, and previous measurements are shown here as significantly lower. So if you feed the CMD3 measurement into the hadron vacuum polarization calculation, you find that the discrepancy between theory and experiment for G-2 becomes insignificant. It's just one standard deviation. Now, I should say that I personally find it a little bit difficult to interpret this result, just because, given the political situation as it is at the moment, it's difficult to, really have a conversation with these people about, why their result differs from previous results, what they think the previous people did wrong, what questions you might have about their measurement. But one could take it at face value. So here I show you a plot which shows you the discrepancy in the anomalous magnetic moment of the muon that you get from the old data-driven calculation, the theory review of 2020, BMW, which reduces the discrepancy significantly, CMD3, which reduces it to a 1 sigma discrepancy, and a recent paper by Javier et al., where they reevaluate some of the previous low energy plus or minus data and say that they think that people didn't do it quite right. So the anomaly in G-2 could be as large as 25 times 10 to minus 10, or it could be 0. So 0 would be great for supersymmetry. At least it would be great for the constrained minimal supersymmetric extension of the standard model, which can only make a very small contribution to G-2. However, you can produce more complicated supersymmetric models, which could give you a non-zero contribution to G-2, and which could, in principle, accommodate any one of these various different theoretical estimates. So this is what we did in a very recent paper. So, as I already said, you can only get a very small contribution to G-2 in the CMSSM. That's because of LHC limits on strongly interacting particles. But if you soften the assumptions in the constrained MSSM, for example, by allowing for non-universal gauge-union masses, or if you allow for non-universal masses for fermions and Higgs fields, then you could accommodate, quote unquote, any value of G-2. So before I go into the details of that, let me just make a general comment. So the LHC tells you that very likely strongly interacting particles weigh 2 TeV or more, although there are loopholes. But LHC data do not exclude lighter electroweakly interacting particles, for example, leptons, for example, muons, which could make non-trivial contribution to G-2. And these are a couple of plots from the Atlas collaboration. Maybe I start off with this one. So these shaded regions are the regions of parameter space, which they say are excluded by their experimental constraints. Possibly some question about that. But there's a region here which they cannot exclude. And this region goes all the way down to a muon mass of 100 GeV. And they thoughtfully provided in the same paper the ranges of muon masses, which would give you a large contribution to G-2, which these bands neatly cross this allowed region here. So this is just making the point that if you take a model-independent point of view, you could have light muons, you could have a substantial supersymmetric contribution to G-2. But of course, if you have a theory in which leptons have similar mass to quarks and gluinos, you can't make a significant contribution to G-2. Now, one other little comment is that the limits that you see quoted in LHC papers often make simplifying assumptions about the reduction and decay modes of supersymmetric particles. In fact, there was another helpful paper by the Atlas collaboration a few months ago, which pointed out that you shouldn't believe their limits in more general scenarios in which more decay modes are allowed. Some ranges of particle masses, which they would have said were excluded in simplified models, are not excluded in more complicated models. So anyway, we went away and looked at a couple of more complicated models in which we basically assume non-universality in supersymmetry breaking gauge-union masses or scalar masses. And so the scales on these plots are too small to be read, so don't strain your eyes too much. But these points are color-coded according to how large a contribution to G-2 you make. And so you could make quite a large contribution to G-2. On the other hand, it could be quite small. The same point is made here. Here what we've got is some dark matter observables. So we've got the overall dark matter density, and we've got the dark matter scattering rate. Now, in addition to these colored bands here, you can also see a very thin orange colored band. That's how large a contribution you can get to G-2 in the constrained MSSM, completely negligible. So I'm not going to go in detail through our analysis. At the end of our paper, we produced some benchmark scenarios which are consistent with all the Atlas limits that we're aware of. So here, the shaded band is the same shaded region that you saw on the previous slide. But here is a channel of allowed masses going down to 100 GeV for the mass of the muon. And these little triangles and diamonds are sample models in our generalized supersymmetric models, which are consistent with the experimental constraints. And these models are designed to be accessible at the LHC. It's just a little bit more effort. The LHC could maybe find an example of a supersymmetric model that could make a substantial contribution to G-2. So that concludes my talk. So here we have this wonderful feat of theoretical engineering, the Standard Model, which is sailing along happily, and it's perfectly consistent with the visible matter in the universe, but maybe below the surface there are secrets in Higgs physics, or dark matter, or the muon magnetic moment, which I think we all hope will soon sink the Standard Model. Thank you.
Hey, Joe. So, will you elaborate the latest spherical model for dark matter that you have been exploring, and what experimental setup that is suited for the test for that one?
Okay. So I spent a lot of my time thinking about looking for dark matter particles at the LHC. This is what I was discussing here, for example. But I'm also interested in looking for other forms of dark matter. In particular, dark matter could be made of waves of ultralight bosons. And this is what I spend a significant fraction of my time thinking about. So one way of detecting that is to use atomic physics. We look for interference between clouds of cold atoms, and those could be sensitive to the interactions of this ultralight bosonic dark matter with components of the atom, so the electron or the quarks and so on. And this is a very, to my mind, interesting, theoretically complementary way of looking at a different type of dark matter from what the LHC could do. I don't know whether that answers your question. There's plenty of other ways to look for dark matter, but it's the other one that I'm working.
still believe that as a supersymmetric particle, like the neutrino, will be one of the candidates for the dark matter?
I still believe in it. So the way I formulate is that I fell in love with Susie over 40 years ago, and I'm a very faithful sort of guy. And although my love for Susie has not been requited yet, I haven't given up hope.
Okay. Any more questions?
So, just a curiosity, in case that CMS will say that the Tevatron W mass is wrong, and instead the standard model value is right, is there any possible theory of new physics where both can be right? Maybe some light particle got produced together with the W Tevatron.
I don't know such a theory. I don't know such a theory.
The Tevatron and the CMS must be both right.
A theory where both can be right.
I think that's going to be very, very tough.
Just a curiosity.
Any more? Tao, you want? Tao, we want to have question?
From both our talks and as well as community studies, there's so many opportunities look into the beyond standard model of physics. And so what maybe your personal opinion that where maybe the next breakthrough that is either you think is likely or you think that we probably should pay more attention to? It's not really a scientific question, but I want to hear your personal opinion.
So I think basically I have no idea. And I think that we're a very challenging moment in theoretical experimental physics where there is no clear direction to go in. So we know that we can produce higher energy colliders if we get the resources. And I'm sufficiently optimistic to believe that somebody somewhere will come up with the money to build a next generation collider of the type that you propose. In the meantime, high luminosity LHC will produce something like 20 times more data than what we have at the moment. The detectors are undergoing significant upgrades. I think the LHC could also provide significant new insights over the next decade or 15 years. But I certainly think that we should have a broader band search strategy than that. And I mentioned in particular this side interest of mine in atom interferometers and using them to look for ultralight bosonic dark matter. There's many other ideas looking for dark matter candidates which are different from what you can find at colliders or the sort of things that you can find in atom interferometers. Axions, for example. So I think generally, in the absence of any definite indication, I would say you look for experiments which give you the largest volume of parameter space, which you can explore.
Okay, any more questions for John? If not, let's thank John again. We should come back by 11 for the talk of Professor Stormian.
try to